acceleration. So if you go down that kinematic scale, you know, position and then velocity is the derivative of position, acceleration is the derivative of velocity, the jerk is the derivative of acceleration. And the reason it's named this, I presume, is because that's kind of what it would feel like. If you're, you know, if you're talking about a change in acceleration, if the rate of acceleration is changing at some rate, that's going to sort of give you that kind of a feeling when that happens. So that's what a jerk is. FYI. Oops. Okay, this one. Just get you just briefly going on this. This is, we're going to do a lot more with this in the future, but I wanted you to just see a couple of these now.
Marty Campbell, I need you to cover in the gold gym, please. Marty Campbell, I need you to cover in the gold gym.
Write the perimeter of a square as a function of side length s. Okay, so that's, we can do that. Well, that's pretty easy. So if I do p, whoops, if I do perimeter as a function of s, what's the perimeter of a square? Side length s. 4s, okay? Got 4 sides of length s, right? Okay, then it wants to know, find the instantaneous rate of change of the perimeter with respect to a side s. Okay, so what in the world does that mean? Okay, that's a little strange. We haven't seen anything quite like that yet. That's a derivative. The instantaneous rate of change of the perimeter with respect to s is just this. That's how we interpret that derivative. This is telling us how fast is perimeter changing with respect to s. And here's how, for now, here's how we can kind of justify that. If I were to look at a graph, and let's just say we're looking at something like area, how about instead? Say we're looking at area as a function of side length s, and it looks something kind of like that, right? If I want to look for a certain value, let's just say hypothetically that this is out here at s equals 10, and the area is 50, something like that. If I want to know the rate of change of area at that point, it's the slope of that tangent line, isn't it? Instantaneous rate of change. How fast is the area changing as a function of the side length at that point right there? Well, it's increasing this fast. Now down here, it's not increasing as fast because the side lengths are smaller. Okay? Up here, it's increasing much faster. The area, in other words, if I were to increase the side length by just a smidge, use a technical term, the area would increase by more here than it would here. Okay? And you can kind of see that in a picture. And I don't want to do too much with this now. We're going to explore this in much, much more detail later, but just want you to have a brief exposure to this. Compare these two squares. Say we got that square, and then we've got this bigger square. If I were to increase the side length, like I say, by just a smidge, so we're going to make this one come out just to there, let's say. I'm not adding that much extra area, am I? Agree? I've just got that little band of red right there that I'm adding. It's not that much. Now, if I increase the big square by the same smidge, look how much area I'm adding. A lot more, right? So would you agree just sort of qualitatively here that the rate at which you're adding area is going to increase based on the side length? As the side lengths get bigger, a small increase in side length gives you a bigger increase in area, right? And so we can see that on the graph, and that's what the calculus does for us quantitatively, right? So if we're looking, if we want to know what this is, we just differentiate p with respect to s in this case. And what would we give for an answer?
I am so confused on what to do with this.
Okay, hang on. Okay.
Oh, boy.
What? Sorry. Okay, so does that make sense? We just differentiate that. That's the answer to this one.
Yeah.
And then if we wanted to evaluate that rate at 1 and 5, there's no s in our answer. Now, the area would have been a better choice. If we were dealing with area on this one, area would have been, as a function of side length, would have been s squared. right? And so DA, yes, the rate of change of area with respect to a change in side lane would have been 2S, and that would have actually changed. That would have probably a better example to use. But then when, when we evaluate that at 1 and 5, I would have gotten 2 and 10, so it would have made a difference. Okay. Last one. No, that was the last one. I think we're set. Okay, head on down. I think we're good to go. Go to the lab, yeah.